Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss square wave potential for free state. Let's begin. The square wave potential for that of free state, when we consider the square wave of one dimensional of depth u naught between x is equal to 0 to x is equal to a, means we consider one dimensional. Let us that potential given as that potential is 0 in which region x greater than a and x less than 0, that is x is equal to 0, that is x is equal to a. In that of region, let we prefer that is region 1, that is region 2, that is region 3. Region 1 and 3 means x is greater than a, x is greater than a, that is the region 3, and x is less than 0, x is less than 0, that is region 1. In region 1 and region 3, the potential will be 0, and in between these two regions, that is region 2, in that of range 0 to a, the potential is u naught, that is the potential inside this, the potential u naught. Now suppose a uniform beam of particles each of mass small m and total energy E is travelling from left to right parallel to x axis, means parallel to x axis, a uniform beam of particles of mass m and possess the energy capital E is travelling from left to right to that parallel to x axis. So what happened in these three regions? One by one we implement the Schrodinger's time independent equation in these three regions. In region 1, we apply Schrodinger time independent equation, means d square psi 1 by dx square plus 2m by h cross square E minus 0, E minus, that is the potential term. In that of region 1, the potential is 0, we use the potential term 0, psi 1 is equal to 0. That treat as a constant k1 square, that is 2me divided by h cross square. The solution of this type of equation, psi 1 is equal to a e to the power ik1x plus b e to the power minus ik1x. In region 2, the potential is inside that of region 0 to a, the potential is u naught. We introduce the potential term here, and we use in that of region 1, we prefer the wave function psi 1, and region 2 we use the wave function psi 2, and region 3 wave function psi 3. So using time independent Schrodinger equation, region 2, d square psi 2 by dx square plus 2m by h cross square E plus u naught psi 2 is equal to 0, k2 square is equal to 2m e plus u naught divided by h cross square. So the solution will be psi 2 is equal to c e to the power I k2x plus d e to the power minus I k2x. In region 3, we prefer the wave function as psi 3 and the potential term will be 0 here. So using that of Schrodinger time independent equation, d square psi 3 by dx square plus 2m by h cross square e minus 0 psi 3 is equal to 0. So that constant will be 2m divided by h cross square. So psi 3 is equal to f e to the power I k1x plus g e to the power minus I k1x. Since look here, no streams is traveling from right to left, there will be no streams that is traveling from right to left, but we consider the beam or the stream is traveling from left to right. That's why that term means g will be 0, there will be no significance of g term, g will be 0. Therefore psi 3 is equal to f e to the power I k1x. Hence, what are these terms indicate? A, B, C, D, F, as these terms are looking like this. We use that region, this region in between x is equal to 0 and x is equal to a. So a e to the power I k1x, that is the incident beam having the amplitude a, that line is a e to the power I k1x. Here that line indicates c e to the power I k2x, that is for f e to the power I k1x. That of reflection way, it will be b e to the power minus I k1x, inside that region d e to the power minus I k2x. Here h is equal to, here that term is equal to 0, that is g e to the power I k1x term will be 0 here, g is equal to 0 here, g term will be 0. Let us, we have to evaluate these amplitudes as a, b, c, d and f. By using these amplitude terms, we can easily derive the coefficient of reflection and the coefficient of transmission. So let us evaluate these amplitudes by using proper boundary conditions. The procedures are same as we discussed in previous conditions. Now the boundary conditions, there are 4 boundary conditions. First two, psi 1 at x is equal to 0 is same as that of psi 2 at x is equal to 0. and its differentiation at x is equal to 0 also same. This is the first pair of boundary conditions. Then second pair of boundary condition at x equal to a and x equal to a. Look here, this is the region. First we use the boundary condition at x is equal to 0, then we use the boundary condition at x is equal to a. In case of x is equal to a, in case of x is equal to a, x is equal to a, psi 2 at x equal to a is same as psi 3 is x equal to a, and its differentiation also at that x is equal to a will be same. These four are the boundary conditions. According to these four boundary conditions, we have to derive four equations respective to these boundary conditions. So what are these equations? First boundary conditions, what is that of wave function? Look here, that is the wave function psi 1 and psi 2. So psi 1 at x equal to 0 is same as psi 2 at x equal to 0. So using that means the first boundary condition we have a plus b is equal to c plus d. Using that first boundary conditions we derive a plus b is equal to c plus d. Again, its differentiation at x is equal to 0. When we implement these boundary conditions for that of wave equations, we get the second equation as I k1 of a minus b is equal to I k2 of c minus d. Third boundary condition, psi 2 at x equal to a, psi 3 at x equal to a. When we implement, we get c e to the power I k2a plus d e to the power minus I k2a is equal to g e to the power I k1a. This equation is derived by using third boundary conditions. Then that equation is derived when we use fourth boundary condition, I k2 whole into c e to the power I k2a minus d e to the power minus I k2a is equal to I k1 g e to the power I k1a. These four are the equations which are derived from these four boundary conditions. Let us we treat the mathematical operations in these equations to get the respective values of a, b, c, d and g. So first we have to add these two equations, equation 1 and equation 2, and then subtract equation 2 from equation 1. When we add these two equations, adding equation 1 and 2, these two pair, there will be 2a is equal to 1 plus k2 by k1 of c plus 1 minus k2 by k1 of d. When we subtracting 2 from a, 2 from 1, we get 2b is equal to 1 minus k2 by k1 of c plus 1 plus k2 by k1 of d. This is 2a is equal to that much, 2b is equal to that much. Again, equation 3 and equation 4 we get when we add these two and subtracting that from this. Adding equation 3 and equation 4, we get 2c e to the power I k2a is equal to 1 plus k2 by k1 of g e to the power I k1a. Therefore, c will be this much, just 2 is divided here. Then subtracting iv from third number, 2d is equal to 1 minus k2 by k1 g of that much. Therefore, d is equal to that 2 is divided here. So you get c and d. C and d means first we have to add these two equations and subtracting 2 from a, and then add these two equations and subtracting that equation from 4. Therefore we get 1, 2, 3 and 4 equations. Here we get the value of C and value of D. Let us put the value of C and D in the respective equation 2A and 2B. Value of C and D are implemented here. What we have? When we implement the value of C and D, therefore 2A is equal to, just implement the value of C and the value of D here, and simplifying it, taking e to the power minus I k2a as common in these terms, in these total terms, and again in that of term we take e to the power I k2a as common, and in overall terms we take g by 2 e to the power I k1 as common. Again simplification, e to the power I k2a plus e to the power minus I k2a divided by 2 minus half of k1 by k2 plus k2 by k1, that quantity e to the power I k2a minus e to the power minus I k2a divided by 2 g e to the power I k1 a. So a is equal to here 2a is equal to that much, a is equal to 2 is divided here, that quantity is known as cos k2a, cos k2a. This is the formula of cos theta, means e to the power I theta plus e to the power minus I theta divided by 2 k2a minus I by 2 k1 by k2 by k2 by k1, that is sin k2 by a g of I k1a. So a is equal to g of this much, therefore a by g is equal to, a by g is equal to cos k2a minus I e, I we introduce a constant c, sin k2a e to the power I k1a. So reciprocal of that, that is g by a will be e to the power I k1a change to that of e to the power minus I k1a. So what is that of transmission current density, that is Zt is equal to h cross by m magnitude of g square, and incident current density 8 h cross k1 divided by m magnitude of a square. So the transmission coefficient, that is capital T, is equal to Zt by J in, that is transmission current density, to that of incident current density, that is G by a magnitude square, means T is equal to G by a magnitude square, G by a magnitude square. So G by a means that quantity. So T inverse will be cos square k2a plus c square sin square k2a, and we use cos square k2a as 1 minus sin square k2a plus c square of sin square k2a. In these two terms, c square minus 1 taking as common, 1 plus c square minus 2 taking as common, that is sin square k2a, where c is equal to we introduce c is equal to k1 half k1 by k2 plus k2 by k1. So c is equal to half k1 by k2 plus k2 by k1. So c square minus 1 taking its square and minus 1, that is 1 by 4, its square minus 1, that is 1 by 4, its square and minus 1, it will be k1 by k2 minus k2 by k1 whole square. And k1, the constant first to implement for that of wave function when we use that of Schrodinger time independent equation. K1 is equal to under root of 2me divided by h cross square. So K2 is equal to under root of 2me plus e naught divided by h cross square. that is under root of. So k1 by k2 that is e by e plus u naught square root, and k2 by k1 is equal to e plus u naught divided by e square root. So c square minus 1, that term c square minus 1 is equal to 1 by 4 k1 by k2 minus k2 by k1 whole square, k1 by k2 minus k2 by k1 whole square. Using these two terms we get u naught square divided by 4e of e plus u naught. That means c square minus 1 is equal to u naught square divided by 4e e plus u naught. So t to the power minus 1 is equal to 1 plus c square minus 1 of sin square k2a. In place of c square minus a, we substitute that term. Therefore t inverse, that means t to the power minus 1 is equal to 1 plus u naught square divided by 4e of e plus u naught sin square k2a. Therefore t is equal to its reciprocal, means 1 divided by that quantity. Basically that term is less than 1. So the reflected probability current density, that is J reflection, is equal to h cross by 2m. This is the wave function term. B e to the power I k1x star means its conjugate dy by dx of b e to the power minus I k1x minus b e to the power minus I k1x dy by dx of its conjugate b e to the power minus I k1x of star, that is h cross k divided by m magnitude of b square. So the reflection coefficient R is equal to J reflected by J incident, that is magnitude of b by a square, magnitude of b by a square. Let us, we have to introduce what should be the value of b by a. To derive the value of b by a, we have to take the value of b. How we get the value of b? So look here, as we get the value of a, when we introduce in that of equation to substitute the value of c and d, again to derive the value of b, again we implement the substitution value of c and d here. So let us use 2b is equal to, here we introduce 1 minus k2 by k1, the value of c g by 2, that much, and again 1 plus k2 by k1 of the value of d, simplifying it in that of similar pattern as we previously done. So finally we get the value of b will be that much, and g is divided here, that is b by g is equal to that much, b by g is equal to this much. But our task is to get the reflection coefficient. Our task is to get the reflection coefficient, and the reflection coefficient is the magnitude of b by a square. So we get b by g here, b by g, and previously we get g by a. So multiplying these two terms, we get b by a, that is g by a into b by g. So multiplying these two terms we get that equation. So the reflection coefficient means the magnitude of b by a square, taking its magnitude term, and this is r, and again t is equal to magnitude of g by a square, as we derived here. T is equal to magnitude of g by a square, that is that equation. So using these two equations we get r plus t is equal to 1. Also r is equal to that much. We introduce the value of this in terms of u naught square divided by 4e of e plus u naught, and the value of t, thus r plus t is equal to 1. This so that the conservation of that probability of flux, that is, so that conservation of probability flux, conservation of probability flux. So, what are the conclusions that are drawn from this squirrel potential for free state? So, the conclusions are drawn. Conclusion 1, when t is equal to 1, that is 100% transmission, that is no reflection occur only if sin k2 a is equal to 0. Sin k2 a is equal to 0 means its general solution k2 a is equal to n pi. So, using the value of k2 here, a is equal to n pi, that of squaring these two sides, we get 2m e plus u naught is equal to n square pi square h square divided by a square. So, e is equal to minus u naught. So, e is equal to this term as e naught minus u naught, sorry, that is e of c is equal to that much, that is known as the critical energy. Again, another conclusions drawn, when t is less than 1, basically t is equal to 1 for the complete transmission, with the transmission resonance at pi, 2 pi, 3 pi, etc. the transmission resonance like pi, 2 pi, 3 pi. So, the transmission is maximum at 1. So, the graph looking like this, the graph is looking like this. This is the graph between E and T. These are the two conclusions that are drawn from that of squirrel potential for that of free state. So, what we studied throughout that of video lecture. So, we studied here the squirrel potential for that of free state. We consider the potential term in between these regions, and using that of time independent Schrodinger equations, we take its solution, and its solution are represented the amplitude terms like this. So, to evaluate or to find out the reflection coefficient or transmission coefficient, we have to introduce its amplitude terms as a, b, c, d, f, g. So, the boundary conditions are taken into consideration. According to the boundary conditions, 4 boundary conditions, 4 equations are drawn. We mathematically operate these equations to derive our respective terms. So, first adding these 2 and subtracting, then adding another 2 and subtracting, and taking the value of c and d in that of equation, we get a. First we get g by a. Here the transmission coefficient is derived, then the reflection coefficient at the magnitude of b by a square. So, again another equations 2b is considered, and putting the value of c and d here, b by is equal to that much. So, b a is equal to g by a into b by g. The reflection coefficient will be magnitude of b by a square, and transmission coefficient is magnitude of g by a square, r plus t is equal to 1 at the value of r and t. So, the conservation probability holds good here. So, what are the conclusions drawn? These are the two conclusions, conclusion 1 and conclusion 2 derived from this. So, with this useful and informative notes, let me wind up this session. Thank you.